correlation doesn't imply causation. So I think all of us probably have said this sentence, or at least thought about it many times, because it's a nice reminder of the difficulties of figuring out what is caused by what. But if correlation doesn't imply causation, then what does? Under what conditions can we detect a true causal effect? So in this talk, I'm gonna try and tease out some of these notions and questions and discuss them on several very practical and concrete examples. So I try to make the presentation with as little statistical jargon as possible. And so I hope that everybody can not only follow, but also participate in the two small questions that I'm going to ask you later using the same quiz that we used before. So let's start with correlation. Correlation, so two variables are correlated when changes in one variable tend to go together with the changes in the other variable. So this plot here shows data with a correlation, because every dot, every red dot is a data point, it's a piece of data. And the x position of the dot measures one variable, and the y position of the dot, so the vertical coordinate of the same dot, measures the other variables. And so since we see that on average, dots that are more to the right, so with bigger x, also tend to be more higher up, so with bigger y, then we call this an instance of correlation. It's not a very strong correlation, but it's still some correlation. Now, what is this correlation exactly? What is this data really? So each dot corresponds to data about one country in the world, okay? And the vertical axis, the y-axis, measures the number of Nobel laureates per 10 million people in that country. So it's like normalized by population, essentially. So that means that the more higher up a dot is, the more people of that country have been successful at winning Nobel Prizes. Just to be a little bit more precise, I'm only counting Nobel Prizes in scientific disciplines, so like chemistry, physics, and economics. Then on the x-axis instead, I'm showing the chocolate consumption in every country. So basically, precisely, it's the kilos of chocolate that on average each person of that country eats in a year. So the more to the right a dot is, the more people in that country eat chocolate, like to eat chocolate, okay? So before we go on, this doesn't really have anything to do with correlation and causation, but I wanted to ask you, can you locate which of these points is Switzerland, okay? So based on the data about chocolate consumption and Nobel laureates. So if you want to try to do that, let me switch back to the quiz. So if you go to the same page, now you find the same plot, the same URL as before, wooclub.com/core2cause, and you can click and select which you think is Switzerland. Some more people want to vote. Remember to click submit. And after you're done, still keep the page open because there's going to be one more quiz for you. Okay, I think almost everyone has voted. So let's see. This is the correct answer up here. So let me show it to you on the other, on the slides as well. So this is Switzerland, okay? So yeah, it turns out that Switzerland used to be leading the world in chocolate consumption, but this is not true anymore. It has been kind of like become average in this, from this point of view. But on the other hand, it's still doing very well in terms of number of Nobel laureates relative to the population, okay? All right, so then this is a correlation, and we have our countries here. And one way to measure the strength of a correlation is by doing a linear regression. So there are other ways of measuring correlation, but that's the one I'm going to use in this talk. So what linear regression means, I'm just going to draw us a straight line that goes as close as possible to the data points. And then a straight line analytically is identified by two numbers. So the intercept and the slope. So the intercept is the 3.0 in this case. And the slope, it's the coefficient that multiplies the x variable, which is chocolate consumption in this case. So basically what this means is that for every, in this correlation, for every 400 grams more chocolate consumed per capita, there is this is associated with one more Nobel laureate per 10 million people, which is not a negligible correlation, I would say. So we're going to do many other correlations, but the basic idea is the same. So I'm going to use the slope coefficient in a correlation to measure, in a linear regression to measure the strength of a correlation. So let's look at another data set, which just off the bat, you see that it's kind of similar. So it's also clearly correlated points. The correlation is not very strong, but still clear. So in this case, the data points, the blue data points now are still correspond each to a different country in the world. And on the y-axis, I'm still measuring the number of Nobel laureates per 10 million people. And the difference is that now on the x-axis, I'm measuring the GDP per capita, so the gross domestic product per capita, which is roughly a measure of the wealth of a country or how the country, how its economy is how much productive is its economy. So now the more to the right a dot is, the more the corresponding country does well economically. And so you see that, again, there's a clear correlation, and these are the countries. So now you see that Switzerland is, well, we already know that does very well for Nobel laureates, and it's also unsurprising, I guess, that GDP per capita is also pretty high. So the if we fit a regression line, we get a similar slope coefficient at 2.5, and in particular, on the scale of this data, that means that 4,000 USD per capita additional GDP per capita corresponds again to one more Nobel Prize per 10 million people. Okay, so now we have seen two data sets that look kind of similar. They have a similar shape on the plane. And we've also seen that they're both clearly two correlations. Then the next thing that I would like to ask you, if you think that any of these two correlations, maybe both or maybe neither, are also reflect a causal relation. So in other words, I'm asking you, whether do you think that eating more chocolate brings more Nobel Prize winners? And on the other hand, I'm asking you whether becoming a wealthier country causes more Nobel Prize winners. So this is the last quiz that I'm going to ask you. So let me switch to the quiz again, and again, same page, and you can rate each of these statements. Eating more chocolate causes more Nobel Prizes, and increased wealth GDP causes more Nobel Prizes, from 1 to 5. So 5 means that you strongly agree, 1 that you strongly disagree, and if you have no clue, put something in the middle like 3. Okay, so here there's no, I mean, I don't have any strong evidence to tell what the correct answer is. But first of all, your opinion is that it's more likely that increased GDP causes more Nobel Prizes, but instead it's fairly unlikely that eating more chocolate causes more Nobel Prizes. And how did you reason about this thing? You probably run a little thought experiment in your head. So you imagine a country that hasn't won many Nobel Prizes, and you imagine to force feed their citizens with lots of chocolate. And then you expect them to do more Nobel Prize level research. Well, probably not. At least it's hard to see a direct connection. On the other hand, in contrast, if a country becomes richer, then it's likely that, so greater GDP, then it's also likely that they have more money to spend on things like education and research, and that might eventually, over the years, have an effect over the chances of somebody winning a Nobel Prizes. So essentially what we have seen is an example of correlation doesn't imply causation. So we have seen two correlations with two data sets that are kind of similar. But in one case, we suspect, we have some reason at least to believe that there is also a cause-effect relation, that was GDP, and in the other case, instead, we are more skeptical about it. So now I have some bad news, because these examples just show that you cannot conclude anything about causation from correlation alone. But then maybe somebody's thinking, okay, but maybe there's a better measure that can measure causal relations from data. And unfortunately, this is not possible, because there are data sets that are essentially identical. So they have exactly the same kind of distribution of data. But in one case, there is a causal relation, and in the other case, there isn't. So the bottom line is that you cannot deduce a causal relation based on data alone. So that's the conclusion. So if you're expecting that there's kind of like a black box that you can put the data in and know if there's a causal relation, causal correlation, no, this doesn't exist. It cannot exist. So this is kind of bad news, but of course, just because something is hard doesn't mean that, or impossible in this case, it doesn't mean that we give up, right? So we can think of a plan B. And so in the rest of the talk, I'm going to tell you a little bit about what we can do with the data about causal relations. The first thing that we can do is we can check the compatibility between some causal model that we have to come up with. So we don't directly draw them from the data, but then we can still do some kind of validation with the data. This is the first thing that we can do. So kind of like compatibility or model checking or validation. This will not always be possible, but when it's possible, it can be very interesting. And I'm going to show you exactly what I mean by qualitative causal model in a minute. Another thing that we can do related to this is once we have reasons to believe that a certain correlation is indeed causal, we also have a way of measuring the strength of that causal relation, essentially of associating a correlation to a causal effect. And so we're also going to do that in a couple of examples. So first of all, what are these qualitative causal models that I was mentioning that we can use to formalize our hypothesis about the causal relations in our data set, and then use the data to partially validate them? So essentially, they are a structural model that consists of a graph, more precisely a DAG, so a direct cyclic graph. So the idea is that the nodes in the graph are the variables that we measure in the data. So in our example, this will be 3 variables: GDP, Nobels, and chocolate, and so you see them on the screen. Then we add arrows to the graph, and so we connect a node to another node with an arrow that goes from the first node to the second node. When we want to represent a model, well, the first node has a causal relation, so causes the second node. So what does it mean in our example? Well, of course, you could write all possible causal relations that you think are plausible and would like to test, but in this talk, I'm going to consider 2. The first one is model M1. And so in the model M1, essentially, is the one that kind of like emerges from from the results of the poll, right? As if we could determine causality by majority vote. But so the idea is that I draw an arrow from GDP to Nobels because I believe that GDP has a causal effect on Nobels. And but I don't draw any arrow from chocolate to Nobels. So I assume that the other correlation is spurious, so it doesn't reflect a causal effect. I'm also going to add, we didn't discuss this, but I think it's reasonable to add, an arrow from GDP to chocolate, because I'm imagining that countries that are more wealthy are probably the citizens of countries that are more wealthy have more money to spend on things like chocolate. It is not really a basic necessity, okay? So this is another plausible causal effect. Then I'm going to also consider another model, and then I'm going to compare the 2 models on the data. So the second model, we add another arrow. So we also assumed in this model that chocolate causes an increase in Nobel Prizes. So I add another arrow from chocolate to Nobels. So once we have built these 2 models, what can we do? We can check for predictions that follow from these 2 models and see if the data confirms or contradicts this prediction. So if we take this model M2, the one with the 3 arrows, then one prediction, one implication of this model is that all variables should be pairwise correlated, okay? And actually, we know that this is consistent with the data, compatible with the data, because we have already seen that there is a significant correlation between GDP and Nobels, and also chocolate and Nobels. And you can also measure the correlation directly for the last arrow, so between GDP and chocolate. and that is also pretty significant. So now in the graph that I'm showing now, I'm gonna plot the slope coefficients of the linear regression, so this simple measure of the correlation strength. And so these are the error bars, and so I'm gonna, so the absolute value of the slopes is different from before, because now I'm doing all the linear regression on standardized data. So that just means that I essentially subtract the mean and divide by the standard deviation, so that I can basically put all of these coefficients on the same scale. But this is just a technicality, it doesn't affect. The point is that we have significant correlations clearly above 0 in all 3 cases. So this is a prediction of model M2, and data seems to be compatible with this prediction. But it turns out that the same prediction, all variables are pairwise correlated, also follows from the other model M1. Because even though there is no causal arrow from chocolate to Nobels, there is still an indirect correlation, so a spurious correlation, that is due to the fact that chocolate and Nobels have a common cause, which would be GDP in this case. So to understand what this means is think about, for example, siblings in a family, okay? So 2 siblings, for example, brother and sister, they tend to have similar characteristics, but it's because one child causes the same characteristics in the other child, right? It's just because they have the same parents, and so they give them both a similar genome, right? And so it's similar thing here. So there can be a spurious correlation whenever there is a common source, a common cause. So now, okay, so basically this prediction doesn't really help us to distinguish, to see if the data confirms one model or the other, one causal model or the other. But then there's other prediction that you can derive. For example, model M1, and in this case, this is a prediction that does not follow from model M2, but only from model M1, is that the residual effect of chocolate on Nobel Prizes is negligible after we control for GDP. So what does it mean here? Essentially it means that if we do now a new kind of correlation, so a new kind of linear regression, where we use now both chocolate and GDP as predictors, and then we use the slope of each of these variables as a measure of the correlation of one and the other on Nobels, then we should find, so that's the prediction, that the one of chocolate, the slope of chocolate, should be something very close to 0. And so if you do this, so these are the slope coefficient, and you see that the measure correlation between GDP and Nobels remains high, quite high, and instead the one from chocolate to Nobels is close to 0, and you see that the error bar overlaps completely 0. Okay, so this is essentially, this means that the data confirms this particular prediction of model M1, and this is not a prediction of model M2. So we kind of have accumulated some evidence that model M1 may be more consistent with the data. Now, somebody of you who are, especially those who are familiar with linear regressions and multiple regression and so on, are probably thinking, okay, so this is pretty obvious, right? So it's also uninteresting. So because what we have done is what I described is something that is called controlling for GDP when regressing on the other variable like chocolate consumption. And this is a standard practice in multiple regression analysis. We can include all the information, all the predictors, so that we reduce the chance of missing the contribution of some variables. However, the problem, so there's a twist now. So the problem is that sometimes, and by sometimes I mean under some causal model, adding a variable to a regression can actually be counterproductive because it introduces a spurious correlation when there was not one before. So in other words, what I'm saying is that whether we should include some variables or not as predictors in a linear regression depends on what our assumptions about the causal models are. And to show you an example where this happens, where adding all the available regressor is not a good idea, let me show you another example from real-world data. So now, as variables, I collected still variables about different countries, but the variables are first the historic GDP, which is essentially the GDP of a country in around the year 1960, which happened to be before the first Ikea shop opened. And well, to be 100% correct, the first Ikea shop opened in 1958, but it took a couple of years to really develop in more shops in more countries. So historic GDP before Ikea. Then another variable is the year when the first Ikea shop opened in each country. And then the number, Ikeas is just the number of Ikea shops today in recent years, okay? Right, so if we, for example, suppose a causal model like this, so we imagine that historic GDP causes first Ikea year because probably Ikea started operating in countries that were wealthier, richer, where people had more money to spend on furniture. And it's also plausible, I would say, that first Ikea year affect Ikeas, because the longer Ikea has been in a country, the more Ikea shops there are today, probably on average, right? Similarly, historic GDP can also be thought about affecting the current number of Ikeas for the same reason, because essentially historic GDP is a predictor of current GDP as well. So here too, we have, first of all, that all three pairs of variables are correlated. So if I measure correlation with the usual trick of doing a single linear regression and reporting the slope coefficient, I find all three correlations are significant. So it's clearly above zero. So now, if we try then to do a correlation with both predictors, so now the thing that we would like to predict is the first year when an Ikea shop was open in a country. And if we use both the number of Ikeas now and historic GDP as predictors, then we find that there's still a significant slope associated with number of Ikeas right here. I see that it's clear above zero. But if this causal model here is right, this is a spurious correlation in the sense that it is not a causal relation. And in fact, if we think about it, it's impossible, chronologically impossible, that opening more Ikea's shops today, which is what Ikea's measures, would retroactively change the year that Ikea first opened the shop in a country, right? So it's clear that this is a relation that is settled, so it cannot be any further causal effect. So another way of looking at the same problem is that if we add the number of Ikeas to the regression as a predictor in this example, in this causal model, we end up underestimating the effect of the historic GDP on the first Ikea year, so first year that Ikea opened shops in a certain country. So then, in other words, this is another example of what I was telling you before, so that to know exactly which variables we should include in our regression to measure a causal effect, we should first have a qualitative causal model in mind, because otherwise the correlation, we have no way of knowing whether the correlations are spurious or not, whether the measure to causal effect or not. Okay, so that's pretty much it. I just wanted to wrap up with by telling you very briefly about where all some of these ideas that I presented come from. So traditional statistics has for a very long time essentially refused to consider any way of determining causal relations other than through randomized controlled trials. So randomized controlled trials remain the golden standard because they effectively isolate the relations that we want to study, but they're not the only way of talking rigorously about causality. And so then some of the ideas that I presented very, very simply today have emerged over the years in various fields that have to deal with a lot of data that is purely observational, like, for example, epidemiology, like in studies of, for example, causes of cancer, or also in population genetics, where they have huge data sets that are purely correlational, and they would like to measure causal effects as well. But the science of causation based on causal graphs, the DAGs that we have seen in some of the examples, and also the related techniques, have emerged much more recently, starting from about the 1990s, and fully developed. I mean, they're still largely being developed, but they became more popular around the year 2000, from the year 2000. And there is one scientist who's most widely credited with these new developments, and it's this guy here, Judah Perl. So, and he's a computer scientist, and in fact, he got to studying causation and causal relations from his research on Bayesian networks for artificial intelligence. So you might also remember that he won the Turing Award a few years ago for his research on causal relations, and his research has been very widely influential also outside computer science for sure. Just to give you an example, this year's Nobel Prize in Economics was given to two researchers for their methodological contributions to the analysis of causal relationships. So they basically did research applied to economics, but along the same lines. So Judah Perl is just an example. This is just a side note of research in computer science and informatics that has been greatly influential in other research areas as well. So computer science used to be considered a bit of less of a rigorous science because of its shorter history and more practical side, but things have changed a lot, and today I think it's the other sciences that greatly depend on informatics. Okay, so 3 takeaways from this talk. First, and that's the main one, you cannot deduce a causal relation based on data alone. You also need to know the data generation process. Second, you can, at least in some cases, partially validate a causal model using the data. And third, you should take into account what a plausible causal model is before choosing the variables to do regression on. And if you don't do so, you risk that your regression may measure correlations that are not causal. Okay, so that's it, and I'm happy to take any questions.